Welcome to the gas laws of Boyle, Charles, and Avogadro. So, if we keep a fixed quantity of gas at a constant temperature, and the volume is inversely proportional to, then the volume is inversely proportional to the pressure. So we can write that this way. So volume, and then we have this this symbol, meaning it's proportional to the inverse of the pressure. So 1 over P. And another way we could write that is by saying, well, the volume is equal to 1 over P times some constant K. And that constant K may depend on some things. In this case, K is a constant that depends on the temperature and the amount of gas present, so the number of moles of gas. So another way that we could write that is then to get K all by itself and say pressure times volume is equal to K, some constant. So what that means is as long as we keep the pressure, as long as we keep the temperature and amount of gas, total number of moles of gas constant, that the pressure times volume is equal to some value, some constant value. Now, we don't necessarily know what that is, and what that value is depends on the temperature and amount of moles, but that means that when we change the pressure, the volume has to change. It has to change in such a way to keep this value constant. So that means that if we increase the pressure, we have to decrease the volume, keeping the temperature and number of moles constant. If we increase the volume, we have to decrease the pressure. The pressure drops. So, what does that look like graphically? Well, that looks something like this. So, if we plot the pressure on this axis, the vertical axis, and volume on the horizontal axis, if we increase the volume from, say, 20, in this case, the unit here is cubic inches. We increase from 20 to 40, that means that the pressure has to drop from whatever this value is, 50 something, 59, down to some lower value, half of that. And so, on the other hand, if we decrease the volume, we have to increase the pressure, because remember, pressure times volume has to be some constant value. Now, we can show that another way. We can have volume on this axis, and now we can plot over here the inverse of pressure, so 1 over P. And now we get a straight line instead of a curved line like this, an inverse plot like that. We get a straight line plot, and the slope of that plot is this value of K. So this is Boyle's law. So as long as temperature and number of moles, so T and N, are constant, that means that we can say that pressure times volume is some constant. So if we change from one set of pressure volume, P1, V1, to some other set, P2, V2, well, P1, V1 has to be equal to K, and P2, V2 has to be equal to K, which means that we can say P1, V1 is equal to P2, V2. Now let's look at an example. So suppose we take a 10-liter balloon at sea level, so let's assume 760 torr, and we bring it scuba diving with us. So if we go to a depth of 33 feet, we'll increase the pressure on our balloon by 1 atmosphere due to the weight of water. So the water is pressing down on the balloon just like the air, that giant column of air above the surface of the water is pressing down, and they're each pressing down. The air is pressing down with a force or with a pressure of 760 torr. The water is pressing down with a force or a pressure of 1 atmosphere. So we have our initial pressure is 760 torr. Our initial volume is 10 liters, 10 point liters, which means we have 2 sig-figs there. We don't know what the final volume is, V2. We want to find that. We know that the final pressure, though, is the pressure from the air pressing down, that should be 760 point, plus the 1 atmosphere, the pressure from the water pressing down. So this is the pressure from the air, that's the pressure from the water. And then here we have a conversion factor to turn atmospheres into torrs, and that gives us 1520 torr, because 760 torr is the same as 1 atmosphere. So we have 2 atmospheres, or twice 760, which gives us 1520 torr. So now, remember, we know P1 V1 equals P2 V2. We can rearrange that to give us V2 is equal to P1 V1 over P2. So we plug in P1, 760 torr, plug in V1, 10 liters, plug in P2, 1520 torr, and that gives us 5.0 liters. Now let's check and make sure that that makes sense. So we've doubled the pressure from 760 to 1520. If we've increased the pressure, should our volume be going down? Because we went from 10 liters down to 5. We've increased the pressure, which means our volume should be doing the opposite because they have an inverse relationship. Our volume should be going down. It did. We, in fact, doubled the pressure. We should have the volume, and we did. We went from 10 to 5 liters. So, that was Boyle's law with the pressure-volume relationship. Now let's look at Charles's law with the volume-temperature relationship. So, if we keep a fixed quantity of gas at constant pressure, then the volume is directly proportional to the temperature. So if we increase the temperature, then the volume goes up. So if we take our balloon and we heat it up, it will expand. If we cool it down, it will contract. So one way we can write that is volume is proportional to temperature. We can also write that as volume is equal to temperature times some constant K. That constant K depends on the amount of gas present, the number of moles, and the pressure. So we can also write that as volume over temperature is equal to some constant K. And you may see where I'm going with this. So, as long as pressure and number of moles are constant, then we can say V1 over T1 is equal to that constant K. But we also know that V2 over T2 is equal to that constant K. So now we can say V1 over T1 is equal to V2 over T2. This is Charles's law. So now we have our initial volume and temperature and a final volume and temperature, and we know that that first ratio has to be equal to that second ratio. So if we plot volume versus temperature with temperature in Celsius, we get a non-zero volume at 0 degrees C. So here is 0 degrees C. We have some various gases over here that we haven't specified the number of moles at. And so we have here the volume, and this is the temperature. So as we cool down from 300 degrees C to 200 to 100, they all decrease, and they're decreasing linearly because the volume is directly proportional to the temperature. So the temperature is dropping, so the volume is dropping, and the temperature keeps dropping, and now we get to 0, but we have some non-zero values. We can go to temperatures below 0 Celsius, and the volume keeps dropping and keeps dropping. Well, what the early chemists found is that there's some point down here at which all of these lines, no matter where we started, no matter what gas we start with, no matter how much of that gas we start with, all of those lines go back to one temperature. That temperature is negative 273.15 degrees Celsius. And what that tends to indicate to us is that there's some value, some temperature at which we probably can't get below, because if we do, that means that these volumes seem to indicate that we should have a negative volume. We can't get a negative volume. It doesn't physically make sense to have a negative volume. You can get a volume of 0, but how do you get a negative volume? Something that occupies less than no space. So, again, it doesn't matter what gas we use, what initial states that we start out with, what pressure, volume, temperature, and N. All of these curves extrapolate to zero volume at the same temperature, minus 273.15 degrees Celsius. And so this is the basis of absolute zero. This is the basis of a new temperature scale that we call the Kelvin scale. So remember, note that there are no inherent absolute zeros to pressure, volume, and moles. There are inherent absolute zeros to pressure, volume, and moles. We can't get below 0 pressure. We can't get below no force being applied. We can't get below 0 volume. It doesn't make sense to have a negative volume. We can't get below 0 numbers of moles. We can't have a negative number of moles of something. We either have none of it or some positive number. So like that, temperature is the same. Temperature has an absolute zero to it. Now, the temperature scales that we normally use in daily life, either degrees Celsius or degrees Fahrenheit, those have a 0 point that we can get below. But there is an absolute zero to temperature as well. There is some temperature at which you can't get below that, just like the volume. And this is because the temperature is a measure of how much kinetic energy the average molecule within a sample has. Well, at some point, that kinetic energy gets to 0. Those molecules aren't moving anymore. That's absolute zero. You can't get less than no kinetic energy. Right? Once the molecules aren't moving anymore, once they have no kinetic energy, you can't take away any more. So you can't lower the temperature anymore. So there is an absolute zero to our temperature. And again, this is why the Kelvin scale is born. So absolute temperatures are measured in kelvins. Note that it's not degrees Kelvin, it's just kelvins. So all calculations that involve multiplying or dividing temperature have to be done in Kelvin, because otherwise you're going to mess up your calculations, because you'll get different values whether you do it in, say, Celsius or Fahrenheit. You could have negative numbers in there. Whenever you're multiplying or dividing, you need to have an absolute scale involved, so it has to be the Kelvin scale. So if we take a 10-liter balloon at 100 degrees C, and we decrease the temperature to 50 degrees C, keeping the pressure and amount of gas constant, what will the final volume be? Now remember, degrees C is not an absolute scale. It's a relative scale, relative to some point that we've arbitrarily defined as 0. That's the freezing point of water at 1 atmosphere. So we need to change those temperatures from Celsius to Kelvin. So to get from Celsius to Kelvin, we need to add 273.15 Kelvin. So 100 degrees C becomes 373, 50 degrees C becomes 323 Kelvin. So we know that we started with a volume of 10 liters. We want to find our final volume. We know that V1 over T1 equals V2 over T2. We can rearrange that for V2, giving us V1 T2 over T1 is equal to, now we plug in our initial volume, 10 liters, our final temperature, V2, 323 Kelvin, divided by our initial temperature, 373 Kelvin, and that gives us 8.659 liters, which then we've rounded because of sig figs to 8.7 liters. So note here that if we look in Celsius, it looks like we're halving the temperature, but if we look in Kelvin, we're not decreasing the temperature by anywhere near half, and so the volume decreases from 10 liters to 8.7-ish. So we're not decreasing it by anywhere near half. If we were to go from 373 to half of that, so 180-ish Kelvin, then we would decrease the volume from 10 liters down to around 5. It would depend on what gas we have. At some point we may condense the gas out if the boiling point is above that 185-ish Kelvin. So that was Charles's law, so the volume temperature relationship. So now let's look at Avogadro's law, the volume number of moles relationship, or amount of substance. So if we keep pressure and temperature constant, then the volume is directly proportional to the amount of gas present. So volume is directly proportional to the number of moles. We can write it that way, or we can write it this way: volume is equal to number of moles times some constant K. The value of that constant K depends on the temperature and the pressure. We can also write that this way: the volume divided by number of moles is equal to some constant K. And again, I hope you see where I'm going with this. So as long as the pressure and temperature are constant, then we can say that that ratio, volume over number of moles, V1 over N1, is equal to that constant K, which has to be equal to that same ratio, volume over number of moles, at some other conditions, so V2 over N2, which means that V1 over N1 is equal to V2 over N2. So that's Avogadro's law. So if we have some chemical reaction that occurs that changes the number of moles, let's say, so we have the combustion of hydrogen in oxygen at constant temperature and pressure. So let's start out with 10 liters of gas initially. So we start out with 2 moles of hydrogen gas plus 1 mole of oxygen gas. So we're starting out with 3 moles of gas. We're reacting that to give us 2 moles of water, so 2 moles of gas. Note that in 10 liters of gas, we may have more or fewer than 3 moles of gas. But the ratio, we're going from 3 moles, for every 3 moles of gas that we start out with, we're going to end up with 2 moles of gas. So we know that we're going to decrease our number of moles. So if we start out with 10 liters, and we want to know how much we ended up with, we don't know how many moles that we started with, but we know V1 over N1 equals V2 over N2, which we could rearrange to give us V2 equals V1 N2 over N1. Well, we know that N2 over N1 ratio is 2 moles of gas being created from 3 moles of gas. We don't know those values, but we know the ratio is 2/3. And that means that we know that V2 is equal to the 10 liters from V1 times that ratio of 2/3. the N2 over N1. So our volume is 2/3 of 10 liters, which is 6.7 liters. Note that I've rounded there for sig figs. So now we have some relationships between pressure, volume, temperature, and amount of gas, number of moles of gas. But we can only vary 2 out of our 4 variables. We have to keep the other 2 constant. So we need some way of combining all of our variables together so that we can change any number of them that we want. And that's going to be the next video on the ideal gas law. So that was the gas laws of Boyle, Charles, and Avogadro.